Phoebe's here. I wonder if that's showing up, the whole board there. Yeah, pretty much. Let's see who else is here. Phoebe, it's just you and me. You got me all to yourself.
Yeah, and I'm driving.
Oh, hey, you be careful.
Okay.
Yeah, you pay attention to the driving. That's the important thing.
Okay.
But there's nobody else on board yet. They're going to show up here at the last minute, I think. So we'll just wait.
I always like to be logged in when I can ahead of time, so at least I'm here.
You are here, and if my IT person can put these on YouTube, you can watch them on YouTube.
Yeah.
Tonight we're going to discuss something called the Biot-Savart law.
Huh.
I have our 8th lab Thursday night. I'm going to write that down. Lab 8. The 8th lab. Wow. Time marches on. The 8th lab is.
Remind me, how many labs do we have?
Well, you only need 10. So.
Okay.
8, 9, 10. But I think there's a schedule for 11, number 11, in case somebody was sick one time. We'll look and see. But I think there'll be a makeup lab for those that maybe they were sick one time. But now the actual name of this lab is it's on Blackboard. I put this lab on Blackboard. It's experiment 14, but it's our 8th lab. I'll put a little TH there. Experiment 14, and it's called magnetic pole strength. And I'm writing this stuff on my whiteboard here. The magnets can have different strengths. That makes sense. Some magnets are very strong, and some magnets are not so strong. And we're going to measure. We're going to measure the strength of our magnet. And the units for magnetic pole strength are newtons per Tesla. That's the unit that you measure magnets in. And we'll talk about that Thursday night. We'll have fun. You guys always seem to enjoy doing those labs on Thursday night. And now there's some homework. Let me write that down. The homework. Today's the 20th of October, and it looks like your homework is homework assignment number 10. It's 1223 on page 577. And 12 1235 on page 578. So you got some homework for me. And you guys took your tests, but I don't know if I've given them back yet. I guess I
Not
did.
this one.
I
Oh
gave
yeah,
them.
sorry.
I gave them back, didn't I?
I think so. I'm not
Yeah.
at home, so I don't know for sure, but I think
Yeah.
so.
I think I gave them back. And there were some good grades. There was a 98, several 80s. There was an 81 and an 80 and an 86. And then there were some other good grades. So you guys did okay. Well, let's see if anybody else is showing up tonight. So far, it's just Phoebe and me, but I'm going to go ahead and I'm going to do my lecture,
Sure.
no matter what, because that way they can watch it on YouTube.
Yeah.
Yeah, but I enjoy it so much more when various ones show up.
Yes. Yes.
I can't believe it. They're not here yet. They're always pretty faithful. It's 5:31 according to my clock.
Well, there was a lot of traffic in Tulsa, so maybe that's got something to do with it. I don't know.
Might be. Hey, Zach is with us. Hey, Zach. Yay, Zach. How's it going? Yeah, he's unplugged. No, that's not right. Unmute. Unmute, Zach, and say hi.
Hey,
Hey, good deal. You're with us. Good deal. Zach's with us.
That's good.
So look here, guys. This is our lab Thursday night. We'll have a great time. We're going to be working with something called a Helmholtz coil. And let's see if I can spell it. It's a Helmholtz coil. And I don't think it even says that here in your lab description, but that's what it is. And if you wanted, yeah, there it is. It says Helmholtz coil. Yeah, it's there. What it is it's two coils. And of course, these are circular coils and they have a radius R. And what's interesting about this particular kind of coil is they have the two coils, identical coils, separated by the same distance R. In fact, so to keep you from getting confused, they'll call the radius A here, and they'll call this distance A, and they'll call this radius here A, and of course this distance here is A. Probably ought to have dash lines on that one. And actually, to give it a little more power, they have 9. They have N equals 9 coils here and N equals 9 coils here. So what they've done is they've wrapped nine. They've gone around 9 times, and they've gone around this one 9 times. Nine times. So I guess that's 18 in all. And that's what a Helmholtz coil is, and that's what we're going to be working with on Thursday night. But we'll try to explain it then. Tonight's topic is the Biot-Savart law. Now, the French have a funny habit of leaving off their final consonants, well, how's that word? Consonant. Yeah, consonant. Like, I'm trying to think of an example. Parlez-vous français? Parlez-vous anglais?
Don't. No, no.
Maybe I'll be better off not to try to speak any of my French there. But see, they call this the Bio Savar law. They don't put the T's on the end. The French is such a beautiful language. You can say ordinary things and it sounds so romantic. Like, for instance, let's see. Je voudrais. Okay, just a minute. Let me think. Je voudrais. Je voudrais. Pour sortir la poubelle. Je voudrais sortir la poubelle. Now, doesn't that sound beautiful? What that means is I would like to take out the trash. So it's a beautiful language. Okay, well, this is all in your Blackboard. That's the word I forgot. Blackboard. This is all in your Blackboard. You can look it up. And this is on Blackboard also. This whole thing here is on Blackboard. You can read about it. And your key to your exam is on Blackboard. Go over your exam, go over the key, make sure I haven't cheated you on it, and if I have, let me know. Like, for instance, each page is worth 25 points. Let's say I forgot a whole page, and you got 75 on your exam. Well, let me know about it, okay? Now, if by some odd chance I goofed up and gave you too many points, don't worry about that. Just forget it. These things happen. But don't let me cheat you. Okay, well, let's see. I'm going to open my textbook here and find this Biot-Savart law and see what we can do with it tonight. It's a little bit.
Or you were explaining something from the lab, weren't you? The A's. You said you were doing the A's and all of that. I was just making sure I didn't.
Yeah, I was telling you about the lab Thursday night, but the description, Zach, the description's on Blackboard, so you can just pull it up and read it.
Cool. All right, that works.
It's on there. I wanted to tell you about this Biot-Savart law. It's a little bit like Coulomb's law. Do you remember we studied Coulomb's law? Come on now. There we go, Coulomb's law. And we derived some wonderful equations with Coulomb's law. Trying to remember some of them, I'm having trouble. But we derived equations for point charges, for rings of charges, surfaces, flat surfaces, disks. We came up with a bunch of different equations. And then we learned about Ampere's law. No. We're going to learn about that tonight. Then we learned about Gauss's law. Now, you might have forgotten Gauss's law already, but it'll be on the final, so you might want to review it someday. But there's Coulomb's law. They discovered that first. And then, here, I'll write it for you. If you write it in terms of electric field, it goes like this. You guys have all seen that many times before. Wait a minute. It just has one Q. There we go. Now, Gauss's law It goes like this. Maybe this rings a bell, maybe you remember. But this was Coulomb's law, this is Gauss's law. And it turned out that you could solve problems a lot easier with Gauss's law than Coulomb's law. But see, Coulomb's was discovered first. Now that's the same thing with this Biot-Savart law. And the way it goes, now it's more complicated. It goes like this. I'm having a senior moment, but it's coming. It's coming. Man, that looks pretty complicated, but we're going to talk about it. That's the Biot-Savart law. Now this dB, that's a small incremental magnetic field. And then we're going to learn Ampere's law, hopefully tonight. And it goes like this. And it turns out that you can solve problems with Ampere's law very quickly and very easily, whereas the Biot-Savart law is pretty cumbersome. I forget which one we did with the Coulomb's law, but it took up the entire board with a bunch of calculus and a bunch of algebra. And then we did the same problem with Gauss's law, and it was just bam, 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 3 little steps and you're done. Well, it's the same way with the Biot-Savart law. The Biot-Savart law is very difficult to use. It's ugly, and I'm going to give you an example here in a minute. We'll go through it. We'll discuss probably the most important equation in the chapter, and that's the magnetic field around a current wire. So if you have a current wire, you've got a magnetic field. And you can find what it is with the Biot-Savart law. You can also find what it is with the Ampere's law. Now, doing it here with the Biot-Savart law takes it'll take the whole blackboard. It'll be ugly. We'll start that in a minute. But doing it with Ampere's law, it's just bam, 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 you're done. See, we're going to find the current around a current, or the magnetic field around a current wire. Now there's a picture of it here. Let me see if I can show you. If I can find this picture. Yeah, here's a lovely picture on page 545. This is what we're going to be doing here for the next few minutes. Let me write down what we're going to do. We're going to find the magnetic field of a current wire. We're just going to have a long wire with current in it. And it creates a magnetic field. Let's see if anybody else is showing. Oh, yeah, Stephen's with us. Hey, Stephen's here. Yay, we got 3 wonderful students so far. We are going to find the magnetic field of a current wire, and there's a lovely picture of it on page 545. If you have your book, you might pull it up and look at it. Here, let me draw you, in case you don't have your book, let me draw it for you. They've got a wire there. And here it is. They got a long wire. There it is. And you got current in it. Yeah, here comes the current. Current is going down this wire like that. And to help you to remember, they put your right hand, take your right hand, put your thumb along the current, and you'll see that the magnetic field goes around like that. Here's some more here. Here's the magnetic field, and it goes around and around and around. Here's your magnetic field. It goes around in a circle. Nice picture there in your book on page 545. See, in chapter 11, let me review what we did. In chapter 11, we found if you had a moving charge, in a magnetic field, there was a force on it. We found the force of a moving charge in a magnetic field. That's what we did in chapter 11. Now, chapter 12 is what we're on tonight. Chapter 12 is, where did this magnetic field come from? How do you get a magnetic field? That's what chapter 12 is all about. How to make a magnetic field. This B here stands for magnetic field. See, chapter 11 was all about forces on a moving charge, or it wouldn't have to be a moving charge. It could be a current wire. You can find the force on a current wire. If you have a current, find the force on a current that's in a magnetic field. That's what chapter 11 was. But chapter 12 is, where in the Sam Hill did this magnetic field come from? Where did it come from? Well, I'll tell you one place it could come from. It could come from a magnet. Just go get your magnet. You probably have a magnet on your kitchen refrigerator. Go pull it off. You got yourself a magnet that you pulled off of your refrigerator. It's got a magnetic field. That's one place to get a magnetic field. But all magnetic fields ultimately are caused by moving charges. Inside that magnet that you pulled off of your refrigerator, there's atoms. And there's motion. There's movement in those atoms. Electrons are moving around the nucleus, right? Yeah. Magnetic fields are caused by moving charges. Or currents. See that current? That's got charges moving in it. See these little pluses? Here they come. That little plus is going, it's going down that wire there. It's a current. And it causes a magnetic field. And that's what causes the magnetic field of a magnet on your kitchen refrigerator. You can't see the movement. You pull off your magnet and look at it. I don't see any movement. I just see this magnet in my hand. But there's movement. The molecules and the atoms and the electrons are moving all the time. Okay. Well, great. Now I've given you an introduction to kind of let you know where we're headed here. And this is kind of complicated looking, but let me explain those terms and then we're going to find this equation. By the way, here's where we're headed. this magnetic field on a wire right here, see that magnetic field? It's equal to mu sub O I over 2 pi r, where r is just the distance from the wire. There's your r, okay? See these circles, they have a radius. Come out here, call that r. There you go. Mu sub O is it's the magnetic constant. It's kind of like that epsilon sub 0. That's what we had with electricity, but with magnetism, it's mu sub 0. It's a Greek letter mu. This was a Greek letter epsilon. I think we had this mu in our lab last, yeah. In the lab we did, and I'll turn back to you. I've got those graded and I'll give them to you here. Okay, well, we got our Biot-Savart law. Oh, I was going to tell you what each one meant. So let me make some room here and I'll show you. And our goal here for the time being is to find the magnetic field of a current wire using the Biot-Savart law. Any comments or questions before we do that? Well, okay. Let me get started on that. Now this is going to be a little bit ugly. It's not that bad. You might enjoy it. Who knows?
I did have a question.
Yeah, go ahead.
I was just curious if there's going to be a, like, okay, so this might sound kind of dumb, but so you're showing us that there's like 2 different ways to work some problems.
Yes.
Is there a reason that we would ever have to use the more complicated Biot-Savart law?
No. I would say no. I would go with the easy way. Doesn't that sound good?
Yes.
Yeah. In fact, you probably don't even need to use Ampere's law. What you need is these equations that are derived from the Biot-Savart or the Ampere's law. Yeah, and that's what we're going to show you. We're going to show you, like for instance, the equation for a solenoid. Solenoids are very important. When you go out there and start your car, you turn the key and it goes boom. There you go. You know what you did? You just connected your battery to your solenoid.
Mm-hmm.
And we're going to show you the equation for a solenoid. And it comes from, well, the easiest way to derive it is with the Ampere's law.
Mm.
But you don't even need to derive it every time you use it. You just need the equation for the solenoid.
Gotcha, yeah.
Okay, here we go. We got a wire here now. Let me draw it for you. Here's a wire, and there's going to be current in it. Yeah, here we go. Here's this wire, and we got current in it. Well, now, wait a minute. I was going to show you all these terms here. Well, I can show you on this. Now, what this DL is just a little piece of the wire there. It's a little length. There's your DL. It's a little vector differential length along your wire. And we're going to pick a spot over here someplace. And it turns out that the magnetic field caused by that little differential length, put your thumb along the wire, see how your fingers come out. That magnetic field, dB, is coming out of the board there. If you pick the spot down here, the magnetic field is going into the board. See, put your thumb along the current. See, the current is along here. The current is going this way. this is just a little differential element. It's a differential length element in the direction of your current. Put your fingers there, and can you see your fingers go into the board here? So the magnetic field, any place on this side of the wire is into the board, and any place on this side of the wire, your magnetic field will be coming out. It's just that for this little teeny tiny piece of the wire, we're going to call that a little teeny tiny chunk of magnetic field. And we're going to integrate it is what we're going to do. Okay, but you also need to know this distance here. Now, what this is the distance from your magnetic field element, and that distance is r. And there's a little vector that goes in the direction that heads towards where you want to find your magnetic field, and they call that r hat. They just put a little hat, like you've got to put a hat on your head. Now you know what this DL is. It's a differential length along your wire in the direction of the current, and this little r hat is a unit vector. It's like I, J, and K, only it's not I, J, and K, because that's not. I goes to the right, J goes up, and K would be coming out. This can be, it's just a generic unit vector. It could be in 3 dimensions, actually. So now you know where this r hat is. Now you know what this r is. It's the distance from your length, differential length element to wherever it is you want to find your magnetic field. We talked about this mu sub O. That's the magnetic constant. It's called the permeability constant of free space. And I is your current. It's going down to the right. So you know each term here. Okay, so far so good. And then this angle here, this is the angle between the DL and the r hat. I'm going to give it a name. I'm going to just call it alpha. I'll make up a name. Did you know when you take cross products, let me write it down for you. The cross product of DL cross r hat, that's a cross product. Do you remember that's equal to the magnitude DL times the magnitude of that unit vector, which is 1. See, the magnitude of I is 1, the magnitude of J is 1, the magnitude of K is 1. Those are unit vectors. Well, the magnitude of that unit vector is 1. But you have to go sine of your angle. In this case here, see the angle between the DL going this way and the r hat, that's that alpha. You'd have to go 1 times the sine of alpha. That makes sense? Maybe? Okay, great. All right. Now, let me try some other things here. Do you see that alpha right there? Let's call this angle here, let's give it a name. Let's call it beta. I can call it anything I want to. This is my derivation. That's beta. Well, did you know that the sine of alpha is equal to the sine of beta? They're what they call supplementary angles. I bet you guys knew this. See if alpha was, what's it look like? Maybe a 120? The sine of 120 is equal to the sine of its supplement. There's supplementary angles. The sine of 60. If you don't believe me, get your calculators. Put in 120 and get the sine of it. Here goes, 120, sine of that. Well, it's 0.866. What's the sine of 60? Put it in there, sine of 60. Well, boy, Jove, it's 0.866. See, they're supplementary. You can put in any supplementary angles like, oh, I don't know, the sine of 55. That's going to equal the sine of, would it be 125? Do those two add up to 180? I think they do. Well, try it. What's the sine of 55? Well, it's 0.819 something. Well, what's the sine of 125? Well, boy, Jeff, it's 0.819 something. See, they're supplementary angles. I haven't lost you yet, have I? Let me see who's
No.
with me. Yeah, I haven't lost you. Yay! We just have 3 students right now, but I haven't lost any of them, I hope. Okay, good. We got that. Now, this distance here is the distance from the wire. It's an important distance. We're going to call it something, call it A. That's a good name for it. Call it A. All right. And call this angle here theta. We've had alpha, we've had beta. We skipped gamma, delta, epsilon, zeta, eta, theta. Wait a minute, no, there's theta. We didn't skip there. There's theta right there. Well, did you know that the sine of beta is equal to the cosine of theta? Because they're complementary. See, this angle theta and this angle beta add up to 90. I could bore you by showing you that say that this beta is 60. Did you know the sine of 60 is equal to the cosine of 30? I bet you knew that. They're complementary. They add up to 90. So we got that now. And see, what we could do is we could put that in here. We could put that in there. Instead of having dl times 1 times sine of alpha, we could have dl times the cosine of theta. I didn't lose you, did I? See, dl times sine of alpha is equal to dl times the cosine of theta. Because sine of alpha is equal to cosine of theta. Yay, good going. Now here's something else. dl is equal to dx. See, this is the x direction, going this way. That's x. Well, dl is just a little incremental distance along the x-axis. That doesn't scare us. So you know what we could do? We could write this term here as dl. We don't need the 1. You don't need to multiply by 1. Never mind. We could call it dx cosine of theta, couldn't we? Yeah. Yeah, this whole term here we could write as dx cosine of theta. We sure could. Now let's work on this distance r here a minute. See, the distance r is the distance from your length element to wherever it is you want to find your magnetic field. See if you can follow this. The tangent of theta is equal to x over a. You see this theta? Well, this distance here is x. From here to here, that's x. And a is this distance from here to here. You all know that the tangent is opposite over adjacent. You're all familiar with SOHCAHTOA, aren't you? I could ask any one of you what SOHCAHTOA stands for. Oh, wait a minute. Let's see. So I'll get it right in there. SOHCAHTOA. I could ask any one of you what SOHCAHTOA stands for, and you could just rattle it off like that. Here, let me do that. Let me show you. I've got an excellent group here. Let's go to my friend Stephen. Stephen, tell the others what SOHCAHTOA means. Go for it. Earth calling Stephen.
I'm here. Sorry, I
Yeah,
had to turn off music.
oh, that's fine. Tell them what SOHCAHTOA means.
Sine equals opposite over hypotenuse.
Man, he's got it.
Cosine is adjacent over hypotenuse,
And he's got it.
and tangent is up over adjacent.
He's by Jove, he's got it down. Stephen knows exactly what SOHCAHTOA is. And see, that's what I'm doing here. I'm saying the tangent of this theta is the opposite side. See this triangle here? The opposite side is x and the adjacent side is a, so it's x over a. Yay, good going. Now, good going, Stephen. And I bet the others could have done the same thing. They know what that means. But you know, I think it's good to go over these basics sometimes. It didn't hurt you any to do that. And now watch this, follow this with me. See if you can get to here, students. X equals a tangent of theta. Can you get from here to here? Can you make it?
Yep, sure.
Yay, good going. Now watch this. This is something you might have forgotten. We're going to take the derivative of x with respect to theta. And I know you did this in school when you were younger and better looking. Well, I should apply that to myself, not to you guys. But what you get when you take the derivative of the tangent is you get the secant squared. I wonder if anybody remembers that. Do you remember that the derivative of the tangent is the secant squared? Now, let me ask one of my
I do.
experts.
I remember that.
Zach, do you remember that?
Yep, I remember that.
Yay, good going. Good going. Now here's what I'm going to do. I'm going to write dx is a secant squared of theta d theta. Can you get from here to here? Can you make it? All I did was just kind of scoot that d theta up there.
Yep.
Yeah, we're doing great. Okay, well, we're about 2/3 of the way done here. We've got this dl cross r hat equals to, I got lost here. It's equal to dx cosine theta. But see, dx is a secant squared of theta d theta. So let me write this. Here we go. I need this room. Now, if you guys are taking notes, you'll have all this that we just did. Now there's that mu sub 0 I over 4 pi. I know there's an r squared there, but I'm going to substitute this. See, that's dx times 1 times cosine of theta. Dx times 1 times cosine theta. But that's equal to dx. No. Dx is a secant squared of theta d theta. There's their dx. But wait a minute, we've got to multiply by cosine of theta. Just a second here. That's the dx part. And then there's a cosine of theta that you have to multiply it by. And then don't forget, you got to divide by r squared. So far, so good. Okay, now let me show you something else here. We're going to take the cosine. Isn't this fun? We're going to take the cosine of theta, and that's going to be a over r. Because SOHCAHTOA, the cosine is the adjacent over the hypotenuse. And so the cosine of theta is a over r. Now see if you can get to here with me. R will equal A over cosine of theta. Can you get from here to here?
Yep.
Yay! Now what I'm going to do is I'm going to put that in here. Now, if you put that in there, you're going to have to square it. And so here's what you'll get. Well, I'm just going to put it in there. I'm just going to erase that r squared and put in this thing squared. So you'll have a squared divided by cosine squared of theta. So we're coming right along. We're almost done. If you come this far, we're almost done. And remember what we're doing. We're trying to find a very important equation for the magnetic field of a straight wire using the Biot-Savart law. Okay, now this goes up in the numerator, and it'll be a cosine squared. Did you know that a secant squared times a cosine squared, poof, disappears? Because see, a secant's 1 over the cosine squared, and when you multiply by the cosine squared, it cancels out and just gives you 1. And you see that a and that a squared? One of those a's go bye-bye. What I'm telling you is this cosine squared and that secant squared cancel out and just give you a 1. And this a cancels out with that a squared and just gives you an a. And here's what you got left. What you have left is mu sub I over 4 pi cosine of theta over a. Did I forget anything? I don't think so. I think that's correct. Okay. Now wait a minute, I did forget something. I forgot the d theta part. That's important. That doesn't cancel out, but that's what you have. Okay, that's an incremental amount of your magnetic field. We've got it down to here, and now here's what we're going to do. We're going to integrate. We're going to go like that, and we're going to integrate all this stuff. Here, let me do it. Let me do it up here where you can see it. To get the magnetic field for this whole wire here, we're going to integrate all the little itty-bitty contributions. It's really a vector, you know it. It's coming out of the board up there. And what we're going to integrate is this right here. We're going to integrate mu sub I 4 pi a cosine of theta d theta. And we need some limits. We're going to go from theta 1 to theta 2. Now, I would put my theta 1 here. There's your theta 1. Angles are always measured counterclockwise. You know that. Angles are measured counterclockwise. And my theta 2, that would be here. Now going that way, it would be a negative angle. See, going counterclockwise is a positive angle. Did you know that? Angles are positive when you go counterclockwise. They're negative when you go clockwise. So we're going to go from theta 1. No, wait a minute. This is going to be theta 1, and this is going to be. No, we can have that theta 1 and theta 2. That'll be all right. I'm getting mixed up here, but I think I'm all right. We're going to go from theta 1. That's supposed to be theta 1. There we go. To theta 2. No. The way I did this on my paper was the other way. I don't want to get fouled up here. Just a minute. I think it's right this way. Okay, guys, here we go. Hey, look, all of this stuff is a constant. Pull it out. You got mu sub I, 4 pi a, integral of a cosine of theta d theta from theta 1 to theta 2. This is a, no, that should be theta 1 and that should be theta 2. I had it backwards. Now, does anybody know the integration of the cosine? What do you get when you take the integral of the cosine?
Negative sign.
Nope, positive sign. The integral of the sine is the negative cosine, but the integral of the cosine is the sine.
Are you sure?
Well, we can check it. What's the derivative of the sine of theta with respect to theta?
Oh, we're doing integrals, right?
We're doing integrals.
I got you.
Yeah. Yep. But it is the sine. And so what you wind up with is mu sub O I over 4 pi a sine of theta. And we're going to go from theta 1 to theta 2. Okay. We're almost done. Here's our last one. We'll have our answer here. I just need some room here. Let me make us some room. We'll leave that Biot Savart law sitting there. It's so pretty. And so the magnetic field for a long wire, or it could be a short wire as far as that goes. It doesn't have to be long. Just the magnetic field for a, well, here, let me write it. It's for a short wire, actually. That's not very long. Magnetic field for a short wire is mu sub I 4 pi a sine of theta 2 minus sine of theta 1. Whoops. Now, if this wire is very, very long, the magnetic field for a very long wire the magnetic field for a very long wire, that's going to be mu sub I over 4 pi a times the sine. Well, see that theta 2 there, you know what? It approaches 90, because if this wire goes for several miles out here, and you draw this line to where the wire's end is, that can you see that angle is, it approaches 90. So you have sine of 90 minus the sine. In this case, if this wire goes on forever, if it's a very long wire, go a couple miles down the road, can you see that this angle here, if you go out here to the end of the wire, that angle basically is minus 90. See, angles going this way are negative. So that's a sine of minus 90 degrees. Now, what's the sine of 90? Does anybody know? Sine of 90. If you don't know, put it in your calculator. What's it say? What's the sine of 90? I can
It's
outweigh
1.
you. Yeah, it's just 1. It's just 1. And now we're going to subtract the sine of negative 90. What's the sine of negative 90?
Negative 1.
It's negative 1. So what we have is 1 minus a negative 1. Well, that's 2. You know what? That 2 is going to cancel with that 4. And your magnetic field for a very long wire This is an important equation. It's mu sub I over, usually they go 2 pi r, where r is the distance to the wire, but you can go 2 pi a or whatever dummy variable you want. It's the distance from the wire to wherever you want your magnetic field. There's the bottom line. Now, what did that take us? I had to keep erasing to make space, but it took a whole bunch of stuff, didn't it? Now, let me show you the same thing using Ampere's law. It takes about 3 simple little steps. Bam, 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 and you're done. See, but the Biot-Savart law was discovered first. Like the Coulomb's law was discovered first. And then later, I couldn't tell you the number of decades later, the brilliant mathematician Gauss came up with Gauss's law, and then the brilliant physicist Ampere came up with Ampere's law. So let's do Ampere's law, and let's find the equation for a long wire using Ampere's law. But now this is still very valuable. This equation here is still good. This gives you the magnetic field for a short wire. We probably should practice that. We probably should give you some numbers to plug in here. We'll do that in a minute. But first, let me show you Ampere's law. There's probably enough room right in here because it doesn't take very much. And we're going to do Ampere's law now. It's in your chapter. You could read your chapter. And it goes like this. Very elegant. In fact, it's one of the 4 Maxwell equations of electromagnetism. One of the goals of this course is to know the 4 Maxwell equations of electromagnetism, and this is one of them. Ampere's law. Gauss is another one. Gauss's law is another one of the 4 laws of electromagnetism. Now, to use Ampere's law, you have to have an Amperian path. Do you remember when we did Gauss's law? We had to have a closed Gaussian surface, like a basketball or a football. It had to be a closed surface. That's what this circle means right here in the integral. It stands for a closed Amperian path. In Gauss's law, that circle stood for a closed surface, but here it's a closed path. Okay, well here let's pick our Amperian path. How about we just pick a circle going around our wire. Here's our wire. Make it a very long wire, and we're going to make an Amperian path going around it with a radius of A. Call it A instead of calling it a radius. It doesn't matter. Okay. Now, we know from experience that there's a magnetic field that follows the contours of this circle that we drew, and it's constant at the same radius r around your wire, so we can pull it out. And what you have is the integral of your path going around the circle. Well, we all know what that is. That's just the circumference of your circle, 2 pi r, or in this case, 2 pi a. So we have b times 2 pi a equals mu sub I. And now we're going to have our bottom line. Here we go. B is equal to mu sub I over 2 pi A. Well, look at here. We just derived the magnetic field for a long wire in what, 3 steps? We started here and we went 1, 2, 3, and we're done. Look, we did it here with the Biot-Savart law, but it took more than 3 steps, didn't it? But wasn't it fun? Didn't we have a good time doing that? Hey, I think Ampere's law is a lot easier way of getting at it. So now we possess the magnetic fields for short wires and for long wires. And we know how to calculate what they are. Well, let's do some actual calculations for a minute. I just need some room here to give you some figures, and we'll let you do it. And then the next topic is going to be the magnetic field of a ring, a circular current in a ring. But right now we're going to do a wire. Suppose you had a long wire here. We'll have a very long wire. It goes on for miles, okay? Goes on for miles. And we'll put some current in there. I'll just make this up. How about 50 amps? There you go. 50 amps. I don't think we get that high in our lab. We get up to 10 amps in our lab, and then we blow our fuses because they're 10 amp fuses in our power supply. But suppose you had a 50 amp current, and we want to come up here a certain distance, I don't know, make something up. What does that look like to you guys? Maybe 10 centimeters? Do I have my, hey, let me measure it. I've got a ruler here and it's, no, that's not 10 centimeters. That's more like about 6 centimeters. That's 6 centimeters. And put your thumb along the wire and your fingers are coming out. So your magnetic field will be coming out at you like that. And you got the equation. It's right here. Here it is. Or here, that's the same thing. You got your equation. I'm going to shut up now for 1 minute. And I want you to find that magnetic field. Go for it. I'll be quiet. You find it.
Can you remind us of what the permittivity of free space is?
Oh yeah. Thanks for asking. Mu sub 0 is 4 pi times 10 to the minus 7 Tesla meters per amp. Okay, go for it. I wonder if anybody else showed up. It's just 3 of my excellent students, but the others can watch it on YouTube, so it's not the end of the world. Well, I got an answer. I wonder if it's what you guys are getting.
I got 8.33 times 10 to the negative 5th.
That's what I got. that's what I got. I've got a magnetic field of 8.33 times 10 to the minus 5 Teslas. Now that's bigger than the Earth's magnetic field. The Earth's magnetic field, if I remember right, is about 3 times 10 to the minus 5th Teslas. So that's bigger than the Earth's magnetic field. We could look and see. Let me look that up. Let me see. I don't want to lie to you if I can help it. Earth's magnetic field. Now, where would that be? I don't know where it would be. I need to write it down someplace. See, that's just from my memory. Okay, that's pretty risky. We're going to look up Earth's magnetic field. And magnetic field, I don't see it there. Okay. Let me keep looking here for a minute.
I don't know what I'm doing wrong, but whenever I try to use the Ampere's law derived equation,
You got lost on that Ampere's derivation?
well, so I just substituted in mu naught and I and put in 0.06 meters for the length, and I'm getting something completely different, and I don't know what I'm doing wrong.
Oh, well, it's 0.06.
Yes, 0.06 meters.
Yeah, here. Well, let me write it out.
So what I did was I have 4 pi times 10 to the negative 7 times 50 divided by 2 pi times 0.06.
4 pi times 10 to the minus 7. Did you multiply by 50?
Yes.
And then did you divide by 2 pi times 0.06?
Yes.
Okay, well, maybe we're wrong.
Yeah, the difference, I use 4. I use 4 pi. So yeah, she's probably right. I divided by 4 pi.
It's not 4 pi, it's 2 pi. This
Okay.
equation has a 2 pi a here.
So 1.667 times 10 to the negative 4.
Yeah, that's what I get now. I mean,
All right.
that's what I've been getting. 1.667 times 10 to the negative 4.
Hey, we might owe Phoebe a thank you point here. I wonder, was it me and Zach that both did it the wrong way?
I don't know.
Yeah,
I'm just
'cause
not
look
even sure
here.
I'm doing it right.
No, Phoebe, I think you're doing it right, and I think Zach and I did it wrong. How about that, Phoebe? You feel better now?
As long as it's right.
Yeah, it's right.
Okay.
It's
Thank you.
right. Thank you for speaking up. Zach, I don't know what we did, but we fouled up somehow, didn't we?
It
Well,
was
what
the
did we
4.
do, Zach?
We used the 4 pi on the bottom. We canceled out 4 pi.
Oh, it's not though.
Yeah.
Now,
I looked
Zach,
at the wire.
there's a 4 pi here if you do that. And let's do this equation together. We'll do that one. There is a 4 pi there, but not on this one. Not on this one. That's a 2 pi. Okay, well here, let's do one of these with this 4 pi thing. I need some room though. And we'll make room. We can always make room. Let's get rid of all that. We don't need that. Okay, now we're going to have a short word, but to make it to make it a little nicer, why don't we do it at the, what they call the perpendicular cross section? Yeah, that's what we'll do. And I'll tell you what, let's do. Let's make these angles 45 degrees. That'll make it nice and easy. And we'll measure this. Now let me get my ruler out and see what I got here. This here is 12 centimeters. So that's 0.12 meters. And this angle is 45 degrees, positive. And this angle here is negative 45 degrees. Because you're supposed to measure angles clockwise, counterclockwise. Okay, great. And of course, if it's 45, then you know that this is 0.12 meters and this is 0.12 meters. Yeah, we're happy. Okay, now we're going to use the magnetic field. Here's our current. Current's coming out here. We can do the 50 amps again, that'd be okay. So we got 50 amps coming along here. And here's our equation. We know our magnetic field's coming out of the board, and it's equal to mu sub I. And this one has a 4 pi r. Well, I think we used A instead of R. And this is the sine of theta 2 minus the sine of theta 1. Okay, well, we got theta 2, that's theta 2. And we got theta 1, that's theta 1. And we got A, it's 0.12. We got I, it's 50. All right, find the magnetic field for this wire. It's 0.24 meters long. And we're finding the magnetic field along its perpendicular bisector. It's got a current of 50 amps. There's our equation. Go for it. I'm going to do it. I want you to do it. We'll see if we get the same answer this time. Well, I've got my answer. What'd you guys come up with? How about my friend Stephen? Stephen, do you have the answer for the magnetic field right there?
I was coming up with 5.89 times 10 to the negative 5.
Well, that's not what I got. Did you plug in 45 here and minus 45 here?
Yes.
I got the same thing as Steven, so if we made a mistake, we made the same one.
You guys are probably right again, and I'm probably wrong. Let me do mine over again, just a minute. It's nice to have very intelligent students.
Oh, yeah, you could have canceled both of those out. But
Okay, I'm getting, guys,
5.89.
you guys were right. See, don't you feel good? You're smarter than the teacher, isn't that good? Did you say 5.89 something times 10 to the minus fifth? Is that what you guys said?
Yeah, that's what I got too.
Proud of you. You guys were right. I fouled up. But we got it. We got it between us. We did good. Now I looked up the Earth's magnetic field. And the magnetic field of the Earth in the Tulsa area now, okay? In the Tulsa area, it's around 1 times 10 to the minus 5 Teslas in the Tulsa area. Well, looky here. This is 5 times the Earth's magnetic field, isn't it? Well, that's kind of interesting. Now, so let's do one more thing on this, and then we'll move on to other exciting things. Suppose this wire was very, very long, and it doesn't just go for 0.24 meters, but it goes, I don't know, a couple miles. I want you to find the magnetic field for that wire if it was very, very long. And the equation, remember, is mu sub I over 2 pi r, or 2 pi a in this case. You don't have the sign minus the sign. It's just, that's it for the long wire. Okay, go ahead. Do that one with me. I'll be quiet. Dan used the 50 amps and the distance of 0.12. I think this is must be what I did the last time. Seems like this is the answer I got the last time and it was wrong. But I think it's the right answer for the very long wire. What are you coming up with?
I got the 8.33 times 10 to the negative fifth again.
Yeah, there you go. I think that's what I got the last time. I was doing the long wire without thinking. Now I want you to compare these. This is 5 point something. This is 8 point something. This is only 0.24 meters. That's only about 1/4 of a meter. Whereas this here, that goes for miles, okay? That goes for miles. And yeah, it's bigger, but it's not a heck of a lot bigger. This is only 1/4 meter, 1/4 of a meter, and this is maybe 10 miles long. Well, it's infinite, really. And you increase the magnetic field, but not that much, you know? From 5.89 to 8.33, considering you had to go for miles, didn't increase that much. Okay, well, we got that under our belts. And the next topic is going to be circular current loops. Circular current loops. But we have some valuable equations we've developed. We've developed this one here for a short wire. You might want to write that down someplace where you can grab it in a hurry. And we got the equation for a long wire. There it is, and we've practiced them. And now we're going to do the circular current loops. Let me see if I can find it here someplace. Circular current loops. Let me shop around. Aha, here it is. This is on page 550. I need some room. We're going to have to say goodbye to the long wires here, and we're going to do circular current loops now. And see, you guys are just doing great. Okay, now this is on page 550, and they have a current loop. There's your current loop, and they're going to have current going around and around. I guess this is in front and that's back behind there. We'll kind of make that faded a little bit. And this is coming down in front. Here you go. Yeah, there you go. It's current loop. And what we'll do is we'll make our little elemental distance dl here. Back to the Biot-Savart law. We'll make our little dl there, and we'll make this distance here, a sounds good. I think they used r, but oh well. It doesn't really matter. It's just a dummy variable. I like a. And we're going to come out here a distance x. And so here's what you have to do. You have to draw this distance r. See, the distance r is the distance from your differential length element that has current in it to wherever it is you want your magnetic field. Now your r hat vector is going that way. And if you take the cross product of those two vectors, you will get a magnetic field vector that's doing this. There's your little incremental differential magnetic field vector caused by the dl cross r hat using the right-hand rule. And if you did one down here, it's really three-dimensional and kind of hard for me to draw. It's the same idea. The r hat now is going this way. The distance r is the same. The r hat's going this way. And if you take a cross product between that dl and that r hat, if you take a cross product, what you'll get is a differential magnetic field vector, a little incremental magnetic field vector going that way. What happens is the y components cancel out. What I'm saying is the sum of all the y components is 0. Can you see that? This has a y component and this has a y component, but they're equal and opposite and they cancel out. And not only that, the sum of all the z components will cancel out. See, z is coming out of the board. See, here's x is going this way, y would be going up, and z would be coming out. And the z's and the y's all cancel, but the x's don't. And so what we want to do is we want to find the total by adding all of the x components. And we know what this is. It's according to the Biot-Savart law, it's mu sub I over 4 pi times r in this case, where you have the distance r, DL is the little differential length along your current crossed with your R hat. Your R hat is a unit vector that goes from your DL to the point where you want to find your magnetic field, and you have to divide by R squared. Well, this is going to be ugly again, but we're going to have a nice result here in a minute. Bear with me, maybe we can get this done and take a 5-minute break. All right, guys, this is going to equal to mu sub O I over 4 pi DL times 1, because R hat, remember, is a unit vector. But when you take the cross product, you're going to have to go times the sine of the angle between them. Well, the angle between these is 90 degrees. Can you see that? It'll be that way for all of these DLs. See this DL down here and this R hat? It's kind of hard. This DL is going into the board. This DL is coming out. And what's the sine of 90? Anybody know? Sine of 90 is? What is the sine of 90? Let me ask. It's just 1. It's just 1. Thank you, Phoebe. So that's just a 1. We don't need it. Just forget it. It's just a 1. Like that 1 there, forget it. Okay, well, we're doing great. Oh, wait a minute. Auga. I forgot my R squared. You know what that R squared is? It's the square root of A squared plus X squared squared. So that'll just give you A squared plus X squared. Well, that's what dB is. But see, what we want is dBx. We want the X component. That's what we want. So we're going to have mu sub OI 4 pi. We've got our DL. And we got a 1 times a 1. And we have this. We don't need the square root. It's just A squared plus X squared when you square it. When you square a square root, you just get the thing inside the square root. But if you want the X component, we're going to have to take, there's an angle here. We'll call it theta. That's a good name for it. We're going to have to take the cosine of that angle theta to get the X component of each one. And we'll add them up. Now that theta there, if you can read my writing, is the same angle as this theta up here. How do I know that? Well, I know that because how do I know that theta there is equal to that theta there? See, that theta and this theta here are complementary. There's a 90-degree angle here, and so that theta and that theta are complementary. So if two angles are complementary to the same angle, well, then they're the same. They're the same angle. Okay, well, great. Now, what's the cosine of this angle, SOHCAHTOA? It's A over R, isn't it? It's the adjacent over the hypotenuse. So let me write that. Here we go. We're getting there. We're almost done. We'll take a break because this is getting kind of old. You're probably tired of all this. mu sub OI over 4 pi. But we'll have a nice equation here in a minute. And we got our DL. And you got your A squared plus X squared. But see, the cosine theta, that's equal to A over the square root of A squared plus X squared. See, that's what R is. R is the square root of a squared plus x squared. Okay, guys, we're going to pull out all the constants. Well, mu sub O is a constant. So is I. So is 4 pi. Those are all constants. You know that a and that x, at that spot, they don't change any as you integrate this. And you know what all that stuff is equal to? It's equal to a squared plus x squared to the 3/2, isn't it? All that is constants. And what do you have left? Well, you got an a. That's a constant. Put that right there. And you have the integration of dl. If you integrate dl around a circle, that's just the circumference. And you know what that is? That's 2 pi a. Okay. So it's 2 pi a. Right. 2 pi a. So let me write that. We got mu sub oi. Is this all coming out? Yeah, I think so. We got mu sub oi over 4 pi a squared plus x squared to the 3/2. And there's an a there. And then, just a minute, I got lost. There's an a there, but there's also an a there, so that's an a squared, isn't it? Yeah. See, when you integrate the dl, it's 2. Wait a minute, what happened to the 2 pi a? Okay, now just a second here. Okay, we got that. There's the a. And then when you integrate this, you got 2 pi a. There we go. You know what? You could get rid of the pi's and those 2's, and here's what you have left. You'll have mu sub O I, get rid of the pi's. There'll be a 2 in the denominator, and there'll be a squared plus x squared to the 3/2. And then you'll have an a squared in the numerator. Guys, I think that's it. Can you find that equation in your book? Look on page 551. Page 551. They have mu sub I r squared. We call a r. It's the same thing. Over 2. They got y squared plus r squared. They had their they had this to be a y-axis, but it's just a dummy variable. It's the same thing. Yeah, we have just come up with the equation for a circular current loop. You're looking at it. Where is it? Yeah, there it is. This is equation 1215. It's on page 551. And it's mu sub I, they have an r squared over 2. They have y squared plus r squared to the 3/2. But it's the same thing as what we did with just changing dummy variables. Well, let me conclude with one last thing, and then we'll take our break. There's an important equation for finding the magnetic field right in the center of your circular loop. And I'll tell you what it'll be. It'll be a magnetic field going like this. See it there? And to get it, all you have to do is put in x is 0. Well, if you put in x is 0, here, let me do that. Got to have some room here someplace. The magnetic field in the center of a circular current loop is mu sub I, that's the current in your circular current loop, A squared, that's the radius of your loop, divided by 2. Now, if x is 0, then what you have is a squared to the 3 halves. Well, what's a squared to the 3 halves? That's just a cubed, isn't it? That cancels out with some of that a up in the numerator, and you're left with this, mu sub I over 2a. Ooh, nice little equation. This is the equation in the center of a current loop of a circular current loop. And you'll find that equation on page, it better be in here someplace. I don't see it. Let me keep looking. Oh, there it is. It's on page 551. This equation is on page 551. It says mu sub I over 2, well, they have 2r. If you want to have A equals R, that's fine with me. But they have mu sub I over 2r. We have now found the magnetic field. See, the question was, well, how do you make these magnetic fields? You make them with currents. And we just did it for a straight wire, for a short wire, a long wire. We did it for a current loop. And we're going to take a 10-minute break. Go stretch for 10 minutes. That's enough of that. And we'll work some problems here in a minute. And the last thing we'll do is solenoids. You need to know about solenoids. Go stretch. Go stretch. 10 minutes. We'll be back. Aruga.
Well, you know,
It's break time.
well, that's good.
They deserve a break.
Yeah.
Do you have more class problem?
Yeah, we just got a little 10-minute break here. I was going to go see if there's something to eat down here.
Yeah. It doesn't have jelly
Pauline.
Okay, well, welcome back, everyone. let's uh, let's practice. Let's practice this equation that we've come up with here. Need a little need a little room to work here, though. Let me just get rid of all this stuff, and we'll practice this. And now the topic tonight is, how do you make a magnetic field? Where's it come from? Well, it comes from currents. Yeah. And one way we just worked on was with current loops. So let's do an example. Suppose you had a current loop like this. There's a current loop. And we'll make a radius of, I don't know, let me measure it. Here we go. I'll just measure it. It's, well, it looks like 11 centimeters. It's 11 centimeters. And we can have our current doing this and going around and around. How much current? I don't know. Let's have 10 amps. We're just about to blow our fuses in our power supplies. But we could easily do that. Now to make a current like that, you realize you're going to have to connect this to a negative and connect this to a positive. Like that. Just connect your power supply positive here, and your little pluses will go this way, and that's the way the current will go. This is behind the wall there. And then they'll be coming in front of us here, and they'll be going around and around. 11 centimeter radius, 10 amps. And let's come out here a distance, I don't know, why don't we come out here about 20, let's go 20 centimeters out here. Now there's going to be a magnetic field here. Put your thumb along, yeah, that's the way it's going. And the way the equation goes is like this. It's equal to mu sub O I R squared over 2. In this case, we'll call this X. The book called it Y. They had Y going that way, but I kind of like having X going that way. I think they kind of got mixed up there. It's okay. See, what the book did is they had X going this way, Y going this way, and Z going that way. The way I'm used to doing it is I have X going this way, Y going that way, and Z going that way. But it doesn't matter, it's the same. And so here's your equation. We'll use X's here instead of Y's. All right, now we derived that equation using the Biot-Savart law. There it is. That's the magnetic field right here at 20 centimeters along the axis of that current loop. Now you know everything. You know mu sub 0. You know I is 10 amps. R is 11 centimeters. X is 20 centimeters. You know everything. Find it. I'll be quiet. You have 1 minute. I'm going to do it. I'm going to see if I can get the same thing you guys get this time. Go for it. Well, I got an answer. I wonder if I did this right. How about one of you guys sharing with me here? Zach,
I got 6.39 times 10 to the negative 6.
that's what I got. That's exactly what I got. Now that's, you know what? That's smaller than the Earth's magnetic field here in Tulsa. It's more like 1 times 10 to the minus 5th Teslas. So I don't know, that's about 2/3 of the Earth's magnetic field. So the Earth's magnetic field is pretty powerful then, really, when you think about it. Okay, great. Now let's find what the magnetic field here is in the center. I think it's going to be bigger. We're going to solve for the magnetic field in the center of the loop. Now you could still use this equation and just put x as 0, or better yet, you can use this one here. This one's a lot easier. I'll shut up. Find the magnetic field in the center of the loop. Go for it. Well, what about let's pick on Stephen. Stephen, do you have that yet?
I'm getting 5.71 to the times 10 to the negative 5.
That's what I got. I think we did it right, Stephen. You know what? That's bigger than the Earth's magnetic field. Here's the Earth's magnetic field. That's what, about 5 times as big? Yeah. Hey, I think that's bigger than this. You know it? It's if you drew it to scale, that magnetic field is a heck of a lot bigger there in the center than it is out here. Can you guys see that? Heck of a lot bigger. See, 5 times 10 to the minus 5th is a heck of a lot bigger than 6 times 10 to the minus 6. See, out here it's smaller, bigger in there. Okay, well, we did current loop. Now we need to talk about solenoids. And this is, go ahead, any comments or questions? Yeah, let's work a problem in the book and then we'll do solenoids. If you're happy, I'm going to erase this. Any comment or question? Okay, well, we'll say goodbye to that stuff. And we're going to do a problem in the book. This is problem 1237. We'll see if we can do one of these in the book. Okay, let me find it now. 1237. Aha, I found it. A flat circular loop has 20 turns. Okay, you know all those equations that we just came up with? If you put the number of turns in front of them, you can still use the same equation. It would look like, well, I don't know which one you want. If you want it in the center, I can remember it, it's pretty easy. It would be mu sub O I over 2 times the radius. But see, if you had more than one loop, like if you had a dozen loops, you're going to have to multiply by the number of loops that you got. Okay, now back to our problem, 1237. A flat circular loop has 20 turns. All right. They're going to wrap it around 20 times. The radius of the loop is 10 centimeters. Okay, well here, let's draw the 10 centimeters. It's 0.10 meters. That's the radius. And the current through the wire is 1/2 amp. All right, here comes 0.5 amperes. Determine the magnetic field at the center of the loop. Oh man, we can do that. I feel confident. We know this is 20. We know this. We know this. We know everything. I'll be quiet, and I'll let you find the magnetic field in the center of the loop. Go for it. Find it, and we'll compare notes on that. Well, I got an answer. I don't know if it's right. How about it? Phoebe, did you get 6.28 times 10 to the minus 5 Teslas?
Yes.
Yeah, well, let's see what the answer book says. Now, this was problem 1237. And I'm going to go to the back and I'm going to see what they say the answer is. 1237. They say it's 6.28 times 10 to the minus 5. That's exactly what they said. We got what the book got. I feel good about that. That was good. Okay. Well, let's talk about solenoids now. Now, in your chapter 12, they talk about solenoids. Now, where is it? Let's see if I can find it here. We talk about Ampere's law. We did that. Yeah, here it is. There's a solenoid. Now, I need a little room here. Well, what a solenoid is you come here and you make a loop, and then you make another loop, and you make a whole bunch of loops. I don't know, maybe 100 of them even. I don't know. You make a whole bunch of loops. This is called a solenoid, okay? You just keep making loops. How many did I make? I lost track. Maybe 10 or 12. And then you come down here. And what you do is you connect this to a battery and you run current through there. And the way I got the current going in, I think the magnetic field is going to be going this way inside. I think the magnetic field is going to go that way. Yeah, that is. Because see, your current is going to be going this way. See the current? It's going to go back behind, and then it's going to come this way. There's your current that way here. And then it's go back behind, and then the current's going this way. And it keeps doing that. And then the current here is going this way. And then finally it comes out of there, and the current goes into the negative of your battery or your power supply. And if you take your thumb and put it in the direction of your current, your fingers will tell you the direction of the magnetic field. Now, the equation for a solenoid goes like this. It's a pretty simple looking equation. That's it. Where N is the number of turns per length. Now, what did I have? I had, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 13. I think maybe I had 13 turns. And what was my length? Well, I don't know. I can measure it here. It was about 14 centimeters. So this N, what it is the number of turns per length. So in this case here, I can't do that in my head. Would it be 0.009 something? Let me see. 13 divided by, no, it would be, like 125 or so, wouldn't it? Let's see. 13.
It's 92.8.
Oh, okay, you're quicker than me. I'm getting there. 13 divided by 0.14. Absolutely right. 92.8, and the units are meters to the -1. It's turns don't have units. That's just the number of loops you got. That doesn't have a unit. But it's the number of loops per meter. So it's 98.1. So we got that figured out. You know what that is. I never told you what the current was, but let's say it's 10 amps. If that's 10 amps, then you can find the magnetic field in that solenoid. Let me do it. Here goes. 4 times pi times 10 to the -7 times 92.8, right? Yeah. Okay. Times, gee, I don't know. Did I do 10 already? Let me do it again. 4 times pi times 1e to the -7 times 92.8 times 10. I'm getting 1.16 or 17 times 10 to the -3 Teslas. Now you can make it pretty and say 1.17 milliteslas if you wanted to. See, that's pretty big. You know what? That's bigger than the Earth's magnetic field. See, solenoids give you a lot of magnetic field. You have one in your car, and when you connect it to the battery, there's a metal piece inside here, and it moves and engages your starter motor, the gears in your starter motor, with your crankshaft, and it turns your motor over. Brum, 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 brum. There you go. It's an important thing in your automobile. But where did they get this equation? Well, they got it from Ampere's law. Let's see if we can show you how to do that. They do it on page 582. On page 582, what they did was they took an Amperian path. They came here. They came out here. It's really in 3 dimensions. Kind of hard for me to draw. And my Amperian path is just a big rectangle. And see, it turns out that there's no magnetic field outside the solenoid. And you don't need to worry about Ampere's law on these legs here of your Amperian path. There's 4 parts of this Amperian path. And you know how the equation goes. This is called Ampere's law. This Ampere's law and if you want to add up all of these terms all the way around, see there's 4 parts of this. So we would have 1, 2, 3, 4 parts equals mu sub OI. Now 3 of these parts give you 0 because there's no magnetic field to speak of outside that solenoid. It acts kind of like a north-south magnet, in fact. And the way the magnetic field lines go on a north-south magnet is they come out like this. They go around in a huge circle and they come back into the South Pole. These do the same thing. They go in a huge circle. But there's nothing out here. Nothing out here. Now there is some magnetic field on these legs here, but the angle between the magnetic field and the distance that you travel here is 90 degrees. What's the dot product? Do you remember the dot product is B ds cosine of theta? And that angle is 90 degrees between this distance here and the magnetic field going that way. What's the cosine of 90? Anybody know? Cosine of 90. I can outweight you guys. What's the cosine of 90? It's 0. And because it's 0, this one doesn't give you any term. This one doesn't give you any term because there's no magnetic field out here. Now there's a magnetic field here, but it's got a cosine of 90 term. The only thing that gives you any part of Ampere's law on the left-hand side is this VDS. Okay, well, we'll pull it out. Here we go. Let me make some room here. We'll pull it out. That B is constant inside your magnetic or inside your solenoid. They call this thing a solenoid. That's the name of it. And what you have here is the integral of this distance from here to here. Well, that's just the length of your solenoid. You want to call it maybe L? That's a good name for it. And so you got B, this term here, the B you can pull out of your integral, and you have the integral of that distance there, which is just L. And this is equal to mu sub OI. And here's something you got to know. This current is the current that penetrates your magnetic, your Amperian path. This is the current that enters your Amperian path. And look, see this wire here? It comes up here and penetrates that Amperian path. This wire here penetrates that Amperian path. Each one of these turns penetrates your Amperian path. So what you have is N times I. So you got N times I, and this is equal to L. So what you have is BL mu sub O I times N, or B is equal to mu sub O N divided by L times I. Now N divided by L is our little friend, little n. See, this is the number of turns per length, and that's what little n is. So we just used Ampere's law to come up with mu sub O in I. We have just come up with the equation for solenoids. Now let's do an example of solenoids. I think I have one here. This is problem 1249. We're going to do problem 1249. Let me erase all this stuff. This is what you need to remember right here. Let me write it nicely for you. We have the equation for solenoids. The magnetic field inside the solenoid is mu sub O in I. Now we're going to do 1249. Let me find it and let me read it and see what it says here. $12.49. I finally found it. Here we go. A solenoid is wound with 2,000 turns per meter. Okay. The little n is 2,000 turns per meter. So we got the little n figured out. Okay. When the current is 5.2 amps, we got the current. The current is 5.2 amperes. What is the magnetic field within the solenoid? Okay. Let's do it. You've got I, you've got N, you know everything. Go ahead, I'll shut up. Find the magnetic field inside the solenoid. Go for it.
The bandwidth on your service is low. Is that 5.2 or 52?
Hang on a minute. It's 5.2. Let me put a little dot there. That's better. Can you read that better now?
Yeah, that works.
Great. Well, as long as Zach's with me there. Zach, what'd you come up with?
I'm still trying to make sure I see it right. I think my answer is wrong right now. Hold on.
Fine. Take your time.
Uh, 1.12.
That's not what I got. I could be wrong though. Let me write it out.
Oh, everything just cleared up. All right, I got a 0.032.
Well, that's not what I got either. You could still be right though, Zach. Now let me do mine over again.
4 times 10. Oh, I forgot my pi.
Put your pi in there. I might be right.
0.261.
That's not what I got. Okay, let me do mine over again.
I got 13.1 milliteslas or 0.013069 Tesla.
That's what I got. I got 1307 milliteslas. You rounded it off to 13.1 milliteslas. That's just fine with me. But I'm going to wait till I hear Zach say, uh-huh. Or Stephen. I want to hear Stephen say, uh-huh. Hey, yeah, I just heard an uh-huh.
All right, I got it.
All right, that's more like it. Okay, now, the last topic that I think we have time for tonight is forces between current wires. Now, on that experiment that we did, do you remember we had a movable loop, and when we put the current to it, it would swing out. There was forces between the wires. It turns out, and that's what we're going to do right now. Let me make some room here. And the topic is forces between current wires, or you could just say currents. The forces between currents. Now, it turns out if the currents are going in opposite directions, say you had a current going this way, and then you had another current going this way, and these are two wires. Let's say they're 1 meter long. Well, that's not a meter. A meter, you know, a meter is a lot longer than that. It's more like, getting close. Getting close. Hang on a minute. I got a meter stick here. Just measure it. No, looky here. Meter, it's longer than my whiteboard. See, that's 1 meter right there. This is only about, I don't know, 65 centimeters. Oh, well. Meter is longer than we thought. But anyway, pretend that's 1 meter, and pretend this is 1 meter. Pretend they're both 1 meter long. They're not, they're only about 65 centimeters long. Now, if you take this one here, we better call this I1 and I2. How's that? Give them names. I1 and I2. Put your thumb along I1. Yeah. And you know what? You're going to get a magnetic field going into the board at the location of I2. Magnetic field is going into the board. And I tell you how big it is. It's mu sub O I1 over 2 pi r, where this r is the distance here between your wires. Well, what's that distance? And I don't know, it looks like maybe about 4 centimeters or so. Suppose r is 0.04 meters. We derived this equation 2 different ways. We derived it with the Biot-Savart law, and it took a half an hour of ugliness. And then we derived it with Ampere's law in about 2 minutes. But go ahead and find this magnetic field. Find that magnetic field for me using this formula. That'll be the magnetic field that's influencing this current wire. Go ahead and find it. Oh, I didn't tell you what the currents were, sorry. Let me give you these currents. Let's say this is our old buddy, the 10 amp current here. But let's have this one be different. Let's have that be, I don't know, 5 amps. How's that? We'll have 5 amps on that one. Go into the left. Okay, now you got your 10 amps, and you can solve for the magnetic field. Go for it. Did you get 5 times 10 to the minus 5 Teslas for the magnetic field going into the board at the location of this wire? And I'm waiting for an uh-huh.
Yes.
Yes. Yeah, good. Stephen, are you still with me?
Yeah, I got
Yeah.
that.
Good for you. Okay, now we found the B. That's it. 5 times 10 to the minus 5. Now we're going to find the force. We have an equation we learned. It goes like this. It goes I, L cross B, if I remember right. You guys remember that equation? The force equals ILB. And the L we decided is 1 meter. And the I, we're talking about this current here. It's 5 amps in this case. And the B we decided is 5 times 10 to the minus 5 Teslas. They're 90 degrees apart. The current's going this way, magnetic field's into the board. They're 90 degrees apart, so that's the sine of 90, which is 1. We can get this force on this wire. Go ahead and get it for me. Go. I'll tell you what I got. I got 2.5 times 10 to the minus 4 newtons. There's a force on this wire of 2.5 times 10 to the minus 4 newtons. But what's the direction of it? Well, to do that, you gotta know how to do that right-hand rule. So you gotta take your L. Now your L vector is going to the left because that's the direction of your current. And the B, this distance is 0.04 meters. And the B is going into the board. You got to take this L, go into the left, and cross it with B. Now what I get is I get a force that's going down. The force on this wire is going down. This wire will try to move away. We did that in our lab. We had, maybe you didn't realize it, but we hooked it up so the currents were going in opposite directions in the stationary wire and in the movable loop. And when you turn on the current, they moved apart, and the movable loop swung away, trying to get away. It was repelled. And the amount of force on that wire is 2.5 times 10 to the minus 4 newtons. Now let's figure the force on the top wire. Now to figure the force on the top wire, we need the magnetic field acting on it. Now see, that magnetic field is caused by the current in this wire. This current's going this way. Put your thumb along there. Put your thumb along there, and your fingers will be going into, you know what? The magnetic field at the location of this top wire is going into the board, and we can figure what it is. In this case, it will be mu sub O times the 5 amps, because it's being caused by this 5 amps, all over 2 pi times your 0.04 meters. Now do that for me and give me the magnetic field acting on the top wire. Go for it.
Why does the I2 affect the top one and not the other way around?
This wire here creates a magnetic field, and that magnetic field is like this. Put your thumb there. It's got a magnetic field that's doing this, and at the vicinity of this top wire, it's going into the board. The magnetic field caused by this wire is going into the board at the location of the top wire. See,
Okay.
are you with me on that?
Yeah.
And what, Zach, what did you get for this magnetic field on the top wire?
I was trying to grab the concept. I haven't done it yet.
That's all right. Well, I got an answer for it, but see, it's different than this. I got an answer of 2.5 times 10 to the minus 5 Teslas.
Yeah, that's what I got.
Yeah. Okay, see, that's different than this. That one was 5 times 10 to the minus 5. This is different. Why is it different? Because you got smaller current. That's why. A smaller current creates a smaller magnetic field. But now let's figure the force on the top wire. You got to use the same equation, F equals ILB. But see, the current in the top wire is 10 amps. So here's our force. This is the force on the top wire. It's going to be 10 amps, that's the current in the wire, times its length, which is 1 meter, times the magnetic field, which is 2.5 times 10 to the minus 5 Teslas. Now do that for me and tell me what the force is on the top wire. Hey, I'm getting 2.5 times 10 to the minus 4 newtons is the force acting on the top wire. It's equal to the force acting on the bottom wire. You know why? Newton's third law says that for every action, there's an equal and opposite reaction. These wires are repelling each other, and the forces are the same. They're Newton's third law forces. Now you can get the direction by looking at this equation. Now the length here This length is going to the right. See how this current's going to the right? And the magnetic field is into the board. And when you cross a vector going to the right with a vector going into the board, you will get a force not going down, but going up. The force on this wire is going up. And it's equal to the same amount. See, this wire has a force on it. It's equal to the same force that's acting on this wire here. But it's going down. They're going to separate. Those wires are going to separate. Now that creates a problem sometimes in winding in motors. Because when you wind, like with solenoids, your currents are all going in the same direction. The currents are all going in the same direction together. And when they're going in the same direction, that creates a force that's trying to bring them together. Well, that's not really that big a problem. That's not that big a problem when if they're wrapped carefully, because they can't really bunch up. It's when they have opposite direction currents when they try to separate. Now they have an equation for this. It's on page 548. Page 548. And they've expressed it in terms of force per length. But let's apply it to this problem here. Let me make some room here. I need some room. This is a nice little equation. It's on page 548. And what it is they figured out the force per length. Now we had a length of 1 meter on our wires. So we'll get the same number for our answer. I would derive this for you, but I'm getting tired of deriving stuff for you tonight, and I'm sure you are too. But let me just show you, you get the same answer. In this case here, you know what that is? It's 4 pi times 10 to the minus 7 Tesla meters per amp. I1 was 10 amps. I2 is 5 amps. And you got 2 pi R, and R is 0.04 meters. Okay, plug all that into your calculator and see if you get the same force. Go for it. Boy, Juve, I'm coming up with the same force. I'm coming up with 2.5 times 10 to the minus 4 newtons. Wait a minute, I'm getting mixed up now. That's a magnetic field. Where's our force? What do we do with our force? Guys, I erased it.
Yeah, I think you had to erase it.
What was it? Does anybody know? My mind just...
No, the screen going blurry for me.
Yeah, it is 2.5 times 10 to the negative 4th newtons.
Yeah, that's right. That's what we got before. I just erased it as the problem. Well, that was on a 1 meter piece of wire. And so you see, that's the force per length, according to this equation, is the same answer that we got. Ta-da! Nice little equation. So now we know that current wires that have currents going in opposite directions repel. Current wires that are going in the same directions attract. We probably should do one of those. Here, let's do one of those. Let me have a couple of wires going in the same direction, and they should attract. This time, let's look at the wires coming out of the board like this. And we'll have a wire here with, I don't know, 10 amps coming out of the board. And we could have this, this distance here. Here's another wire coming out of the board. Why don't we have it 10 amp also? We got two wires, they're parallel. And we think that when you have the same direction, there's going to be an attraction. There's going to be a force attracting that wire and a force on that wire being attracted to that wire. Okay. Now I showed you two ways to do this, but let's do it the hard way. Now the hard way is you put your thumb there, and can you see that you're going to have a magnetic field equal to mu sub O I over 2 pi r. I never told you what the r was. Well, let's measure it. It looks like about 12 centimeters. There we go. So we can get that magnetic field. What about the magnetic field on this wire here? Well, let me think now. Put your thumb here on your right hand. Whoops, no, it's coming this way, isn't it? You know what? I think the magnetic field on this wire is going this way, don't you? Yeah, it's going this way. But we're lucky, since they both have 10 amps, they both have the same magnetic field. Go ahead and get that magnetic field. Go for it. I wonder if you got what I got. I got 1.67 times 10 to the minus 5th Teslas.
Yep.
Yeah, good going. Now let's figure the force. Now to figure the force is, how does it go? It goes I L cross B. Okay. Well, let's do the force on this wire here. Well, the I is 10 amps. The B, the L is, well, let's say it's a 1 meter wire. And the B is 1.67 times 10 to the minus 5 Teslas. And so what's the force on it? I can almost do that in my head. It's 1.67 times 10 to the minus 4th newtons for that 1 meter. If you wanted newtons per meter, just divide by meters. But you're going to get the same force on this wire here. But let's get the direction. Now this length here is coming out of the board, and the magnetic field is going up. Now, if you take the cross product of that, I think what you'll get is a force going to the left. There it is. Now, if you do the same thing on this one, the IL cross B, the L on this one is coming out of the board also, but the B is going down. Now, if you cross something coming out of the board with something going down, you get a force going to the right. There it is. And that force will be this. Now you can use this other nice equation if you want. You get the same answer on page 548. The force between those wires is equal to mu sub O, I1, I2, 2 pi r. Let's put it in our calculators and see what we get. We know mu sub O, I1 is 10, yeah, I2 is 10, 2 pi r is 0.12 meters. Do it. What do you get when you do that? Let's try it. Well, I get 1.67. Now, wait a minute. I didn't get the same answer. I must have done something wrong. I got 1.67 times 10 to the minus fourth. No, that's what we got. It's the same answer. See? You get the same answer using that equation there. Okay, well, great. Any comments or questions on that? Well, let me tell you one last thing here. And that is there are 3 types of magnetic materials. At the end of your chapter, see, not everything has magnetism. Like if you take a piece of plastic, it doesn't stick to your refrigerator very good because it doesn't have any magnetism in it. It's not a magnet. But there's 3 kinds of magnetic materials. And at the end of your chapter, let me tell you what they are. We got 5 minutes, so let me tell you what they are. Not all materials are magnetic. It has to do with the unpaired electrons. In chemistry, I don't know if you remember taking chemistry. Some molecules have electrons that come in pairs, and some don't. But there's 3 types of magnetic materials. Or magnetic substances, you might say. There's paramagnetic, there's diamagnetic, and there is ferromagnetic. And they are explained. I see it here on page Well, I see it on page 566. Page 566. Now let me see if I can remember how this works. That's interesting. Water is a diamagnetic material. Animals are mostly composed of water. Did you know that your body is mostly water? And water is diamagnetic? Well, what does that mean? Well, it means that it's got a very, very faint magnetic property. Now iron is ferromagnetic. Water is diamagnetic. Iron is ferromagnetic. I'll tell you this about iron. You can take a solenoid. We talked about solenoids. And you have a lovely equation for solenoids. And if you put a piece of iron inside one, like a nail, just go to the hardware store and get a nail and stick that nail inside your solenoid. It will increase your magnetic field by a factor of, gosh, I don't know, sometimes 1,000. Does it tell you that? Let me see if I can find it here. I don't see where it says it here. But it will do that. It will increase your, before you had a magnetic field equal to mu sub O Ni. But when you put that nail in there, and you can easily multiply that by 100, very easily, with that nail in there. My wife's uncle was an auto mechanic, and he lost a little screw down in the shaft there that goes to the distributor. And doggone it, how are you going to get it out of there? You don't want it down there, it could cause trouble. So he took a long screwdriver and wrapped a wire around it and zapped it to his 12-volt battery. That magnetized that screwdriver. He stuck it down in that well, and it attracted that screw, and he pulled it out. Pretty clever, huh? Pretty smart. Okay, now what about these here? These diamagnetic, paramagnetic and diamagnetic. It turns out that all materials are somewhat paramagnetic. What they do is they will decrease your magnetic field. If you put a paramagnetic substance in a magnetic field, it decreases the magnetic field. And it has to do with the unpaired electrons in that material. Diamagnetic materials will increase the magnetic field when they're placed in a magnetic field, but nothing like iron. Iron, it's in a world all of its own, and it increases the magnetism. But I'm not going to test you on that. But it's interesting to know that there's 3 types, and your body is composed of water, which is diamagnetic. Okay, well, guys, we had a lot of fun, and it's sad, but our time together is over for tonight. but I'll see you Thursday night for a lot of fun. And what do we got left here? We got our 3 faithful students, Zach, Stephen, and Phoebe. Proud of you. And I hope
Thank
the others, yeah, thank you guys. I hope the others will watch the YouTube. Hey, see you soon, I hope. Bye-bye, everyone.
Bye.
Bye-bye.